Hi guys, today we're going to continue our discussion about families of graphs and graphical transformations. So we've started this by just talking about how an absolute value graph gets transformed, but really everything that we learned applies to any kind of graph out there. So here we're just going to write this in general. So assuming that C is just any number that's bigger than 0, what would happen to a graph if I took my function and I just added C units onto it? So for example, what would happen if I have the absolute value of x and I add some number 3 to it. So this particular example, that plus 3 would make the graph go up 3. So if I added just any number c, it would make the graph shift up c units. So now if instead of adding c, I subtracted c, it's a similar idea. We're going to shift down C units. So now this is a little bit different. Here what I'm doing is I'm adding the C just to the x, not to the entire function. So to give you an example of what that would look like, it would be like when I added something on the inside of the absolute values. So for this particular example, that plus 3 on the inside of the absolute values would shift the graph to the left 3 units. So the same thing would happen if I just added c to the inside of the function. So this would shift to the left c units. And now if I were to subtract c, it would be the other way. I would shift the graph to the right C units. So now here's the one that's a little bit harder. So here this affects how stretched out the graph is when I multiply a number in the front of the function. So for example, if I had something like 3 times the absolute value of x, hopefully you remember from yesterday that 3 affects how stretched out the graph is or how skinny or wide the graph is. So when that number c is bigger than 1, that means that I'm going to make the graph skinnier. If the number c is between 0 and 1, then that means I'm going to make the graph fatter or wider. So what we're going to call this, the skinniness of the graph, we're going to refer to as a vertical stretch. So here this c is going to be a vertical stretch. It's going to be a vertical stretch by a factor of c. Now here we talked about the graph getting wider. So that means that this is going to be called a vertical compression. Meaning that I'm going to squish the graph down by a factor of c. Hopefully you wrote all this down for your notes. You didn't rewind. Okay, then the last one is if I have a negative multiplied on the outside of my function. So for our absolute value example, that was when we had something like that. So what that did was we had a reflection here over the x-axis. So now here's a bunch of different paragraphs that you could apply all these concepts to. We've already done the function, the absolute value of x, and we're not going to see these 3 in this course. You'll work on them in pre-calculus. But we are going, well, not too much at least. We're going to work on this one in this chapter. That's what we're going to start focusing on. So if we have the function, just f of x equals x squared, it does the same thing. The transformations are all the same. So that is all going to be a review. We're just going to apply it to a new function. So before we get started with that, I just wanted to make sure that you were comfortable graphing the equation y equals x squared. If you ever don't know what an equation looks like, what a graph looks like, just plot points. So here let's try to plot a few points. I have -3, negative 2, negative 1, 0, 1, 2, 3. So if I just take these numbers and plug them in for the x of that equation, all I'm doing is squaring the number. Negative 3 squared is 9. Make sure if you type that into your calculator, you're putting the negative 3 inside parentheses, or just use common sense and know that a negative number squared is positive. Negative 2 squared is 4, negative 1 squared is 1, and so on. So now all I'm going to do is plot these points. I have the point negative 3, 9, the point negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. Now if I connect these points, I get something that's called a parabola. So this graph, y equals x squared, takes the shape of a parabola. It kind of looks like a U. So here let's try to get the equation and describe the transformation from the paragraph. So here the first one is y equals x squared plus 3. So here I have something added on to the end of my function. So that's going to shift my graph up 3 units. So it was at 0, 0. If you look at this previous example, the vertex of this was at 0, 0. The vertex is just where it turns around. So the vertex of this graph is just going to be moved up 3, from 0, 0 up to 0, 3. So now, for right now, we're just going to be doing a rough sketch of this graph. So we're just going to make a U shape from this. We're going to get into a more detailed sketch as we move through this chapter. This is just an intro. So now let's do this one. Y equals x squared minus 7. So this minus 7 makes the graph shift down 7. So instead of being centered at 0, 0, it's going to be centered down 7 units at the point 0, negative 7. And it still has the same shape. It still has a U shape. So before we move on to the slide, I would like to name the student of the day, and that student is Julie Campbell for giving us the idea of having a student of the day. So congrats, Julie Campbell. Okay, so let's try to graph these equations and describe the transformations. So now this minus 1 is on the inside. It's just happening to the x. It's not happening to the entire equation. What I mean is that this is not the same thing as this. So in this equation, the minus 1 is on the outside of the whole function. On this one, the minus 1 is just happening to the x. That affects the type of shift that we have. In this particular example, this shift is a horizontal shift because I'm subtracting. This is a shift to the right 1 unit. So now instead of my vertex being at 0, 0, my vertex is at 1, 0. I'm just going to draw my parabola from there. So now let's try this one. This is a different case here. I have a negative on the outside of my function. So this is similar to when I had that type of absolute value graph. So when I have a negative on the outside of the whole function, it gets reflected or flipped upside down. Reflected over the x-axis. So when my graph used to look like this, it's now going to flip upside down and look like that. It's still centered at the same spot. So here I have an upside down parabola. Same shape though. So let's just try a couple more examples where I have a I have a stretch or a compression. So here we're going to multiply our whole equation by a number. If I multiply my whole equation by a number, this is similar to when I multiply my absolute value by a number on the outside. So because this number is greater than 1, this is a stretch, meaning that it gets skinnier. It gets skinnier by a factor of 2. So our vertex is still at 0, 0, but instead of going up 1 unit, I'm now going to go up 2 units for that first point. It's not that way for the other points, but just for that first point. So my graph is skinnier than normal. I also would like to tell you guys a little joke for our joke of the day. I don't even remember it now. I cheated. Our joke was, what did the baby corn say to the mom corn? Where's popcorn? All right, last example, then you can answer your questions and be done. So here, because this 1/3 is a number that is less than 1, this 1/3 would have a compression of our graph by a factor of 1/3. So my vertex is still at 0, 0. But instead of starting with the point up 1 over 1, I'm going to go up 1 and over 3. And same on the other side. So this view is now just very wide. I would just like to give you guys a disclaimer that here we are only trying to make a very rough sketch of the graph. We will go into a more detailed graphing later in this chapter. I just want to give you guys an idea about how compressions and stretches work. Thanks for listening. Don't forget to answer the questions.